All right, hello. Welcome to the November seminar for the Pitt AWM Student Seminar series. For this first talk, we'll be welcoming Rahnuma Islam from the University of Pittsburgh. Thanks for being here. Thanks for the talk.
Yeah, thank you so much for inviting me. Today I'm going to talk about discrete time and continuous space model that I built with Bart Armentrout and Sabrina Stripert. And that model was able to actually produce some of the pigment pattern that we can see in a mollusk shell. Okay. So the shell pigmentation is actually coloration or marking on the shell surface. Usually that is actually created by the mantle, that is a tissue along the edge of the shell that actually deposit the shell materials and pigmentation as the shell grow. So these create a wide variety of pattern formation, as you can see in those picture. Some are spots, some are actually in a wave. There is also checkerboard pattern. Some are more complicated pattern we can see in those mollusk shell. We are going to show that we build a local excitation and lateral inhibition neural model that actually generates some of those diverse patterns through dynamic bifurcation. So the presentation is that first I will talk about that why we are actually taking this approach of neural model. Second, I will talk about that why, how did we build those neural model. Then linear analysis and bifurcation analysis will identify some of the condition based on which those bifurcation happen. And at the end, I'm going to show some of the simulated pattern from our model that actually similar to the shell pattern that we see in the mollusk. The first thing is that why neural model? You can actually use the reaction diffusion model or cellular automata model that would be also able to actually generate those pattern. We take the neural model because pigmentation is not actually random. It is deeply tied to the nervous system of the mollusk. So that is why this is more actually biologically sustainable using this neural model. So in this picture, you can see the actual anatomy of the shell. These actually in orange, this actually hard exoskeleton, that is the shell. And in under this shell, this soft part, that is the actually tissue that is called mantle, which is actually connected to this nervous system, brain. Better picture of this actually cross section of this one. This is the shell. This actually in orange. This is actually in hard exoskeleton shell. Under this shell, you can see that those are neurosensory cells. So what happened? Those neurosensory cells read the actually pigmentation that has already been occurred and send that signal to the neuron. In the picture, you can see those nervous system of the mollusk cell in this actually pink. And then neuron receive those stimuli from neurosensory cells and send the response to the secretory cell. You can see in the picture this dark green color, those are the secretory cell. Then secretory cell deposit the next layer of the pigmentation. So that is the basic structure of the nervous system, how it actually works to deposit those pigmentation. And learning about those neural model has actually benefit for that can lead to the actually broader question of the neuroscience, evolution or development biology. So next thing is that derivation of the mollusk model that we did. So the first thing is that we assume that space, that is X, is along the line of the secretory cell. And there is this time the pigmentation occurs actually sporadically rather than actually continuously. So that's why we use the discrete time step. This is actually basically this pigmentation is actually one-dimensional in a process. We are looking through a two-dimensional process, the space and the time. So suppose this is the actually previous pigment deposition, then the neurosensory cell will read that and they will send the stimuli to the neuron. We have two types of neuron. One is excitatory and inhibitory. So excitatory stimuli that they will receive from neurosensory, we use the function WE, and for inhibitory, this is WI. Then excitatory and inhibitory will respond to those stimuli by this function E and I. So then the net stimulation that we will get from the neuron, that will be given by this function f of x. And then that will be sent to the secretory cells, and then secretory cell will actually deposit the next layer of pigmentation. Okay, so this process will actually repeat again and again until the actually pigmentation occurs, and we're going to use this P of X to denote the actually pigmentation that happened at time T at this location X. So suppose Pnx is the actual amount of pigment secreted at time t equal to n and at the location x, and f is the response to this stimuli, then this is our equation of the actual pigmentation that will occur in the next step of the time, Pn plus 1. Here, this En plus 1 is equal to this function, convolution integral, and this In plus 1 is equal to this convolution integral. Here, this WE is the excitatory kernel, and here WI is the inhibitory kernel, and this P is the actually pigmentation from the actually previous step. Okay, so this excitatory kernel and inhibitory kernel, how we define this one is that we actually use the actually Gaussian kernel for these two, for this excitatory and inhibitory. This is the actually diagram for the actually Gaussian kernel. It shows that if a cell is excited, then the actually in effect of this cell to nearby cell would be greater than the cell that is far away from. So the distance between two cells will actually determine what is their neural effect to each other. The more they are actually close to each other, the more effect they will have. So then we had to separate the actually space and the actually time to do the analysis. So this is the filter that we use, that we are actually separating those actually kernel for x times for the actually time. So this x a kernel, the actually condition is that that have to be symmetric, and BL have to be decreases as the J would be actually larger. So then we defined that this is our space kernel, where this alpha L is the actual amplitude of those neurons, and this sigma L here are the actually lateral ranges of those neurons. And then we defined the actually temporal kernel by this function, beta to the power j times 1 minus beta, separate for excitatory and inhibitory, that beta have to be less than 1, so that it decreases with larger j, and also it satisfies this condition. Here, this beta are the decay rate of excitatory neuron and inhibitory neuron. So then our final simulation model become into this one. So this is our actually pigmentation at the next step. That would depend on this function f. F of this whole thing here, those are special kernel, and this SE and SI are actually given in the second line, and those SE and SI are the actually simulation that they read from the actually previous pigmentation. So then this response function f, we actually consider the response function to this one here, this mu1 and mu2 give you the sharpness of the linearity. And this theta1 and theta2 give you the threshold of the nonlinearity. If the response function exceeds this threshold, that's when the cell will be excited and the pigment would be deposited. So depending on this theta2, this f of x takes two type of form. If theta2 is finite, this kind of look like this. So we call it a bump nonlinear function. You can see that this is actually sharpness. This is mu1, and there is another sharpness. This is actually mu2, and it actually crossed the threshold here here, and then again it actually go down of the actually a threshold on this side. So those are theta1 and theta2. And if theta2 is infinite, then this f of x takes the form of the usual sigmoid function. You can see that there is this sharpness of this f of x, and this is the actually threshold. Once the f of x exceed those threshold, that's when the actually pigment deposit. So the next thing is that since we want to know that when or how the actually bifurcation happen, we want to know that when the system get actually unstable. So we actually perform the linear stability analysis, and we got our actually characteristic equation by this one, where where a of k is equal to this equation and b of k is this one. Here, these actually a capital Ke and Ki are the actually Fourier transforms of the spatial actually kernel that we see in the actually previous slide. And this gamma, this actually parameter is very important. This actually gamma, this is bifurcation parameter. Later in our analysis, actually we use this gamma, and we see that if it goes above our threshold, that's when the Turing bifurcation happen, or Hopf bifurcation happen. So the solution of this characteristics equation, lambda will indicate whether the actually perturbation will decay or grow over time. So the system is stable if this lambda, if the solution of this characteristics equation is less than 1 for all k. So that means that it have to satisfy the Jury stability condition. There are three conditions. The first one is that if lambda is equal to 1, then this actually a characteristics equation is positive. If for lambda -1, this characteristics equation value would be also actually positive. And the third condition is that b of k have to be less than 1. So next, now we will talk about that what happened like when the system is actually unstable. The system will be actually unstable if any of these Jury stability test is violated. Okay, so another way to say is that the root of lambda will actually cross the unit circle. So this root will cross the unit circle in 3-way, and that's what I'm going to talk about in the next one, that is the bifurcation analysis. So here this solution, the system would be unstable when lambda actually leave the unit circle into 3-way. One is that through lambda equal to 1, another one is through lambda equal to -1, and another one is lambda equal to e to the power I in I5. So when it leaves the actually circle through lambda equal to 1, this is when the first Jury stability condition is violated, and that is when the Turing bifurcation happen. Turing bifurcation or the spatial bifurcation happen. And the condition that we find out for this actually bifurcation, that gamma have to be greater than this actually of this expression, which we say that it is equal to actually gamma t. then this actually gamma t is the Turing bifurcation or a spatial bifurcation threshold. And next, this type of bifurcation usually will lead you to the actually pattern that looks like vertical stripes, orthogonal to the mental age of the mollusk. And the necessary condition for this type of bifurcation, what we find out that sigma I, the actual spread of the inhibitory, have to be larger than the spread of the excitatory. Then the second bifurcation is that when lambda actually cross the unit circle via this -1. This is when the second condition of the jury stability test is violated. This is when flip or period doubling bifurcation occurs. And the condition is that this gamma have to be greater than this expression, which we say that gamma f. And this is similar to the condition for the Turing bifurcation, but we did not explore this actually condition any further because this bifurcation does not actually give us any pattern. And the third one is that when the bifurcation happened, when the root of lambda leaves the unit circle through this way, this is when the third condition is violated. And this one gives us Neimer-Sacker bifurcation or Hopf bifurcation occurs. And the threshold for gamma is that this expression. And if actually gamma exceed this threshold, gamma ns for k equal to 0, then the temporal bifurcation happen. That usually give you the horizontal stripe. And if gamma exceed this threshold for k is greater than 0, then the spatiotemporal instabilities occurs. Usually we get wave, checkerboards, spot pattern, or more actually complicated or more complex pattern from this one. So the necessary condition that we get here is that usually the decay rate of the excitatory have to be larger than the decay rate of the decay rate of the inhibitory have to be larger than the decay rate of the excitatory. So next, after we find out the actually condition of each bifurcation, we also want to know that in which bifurcation will actually cross this threshold first, right? Whether the actually gamma will cross the threshold of this Turing one or the actually Neimer-Sack one. So this one said that gamma t, that's mean Turing bifurcation will actually occur for k equal to 0 when this one satisfies this condition. So d have to be less than d star, where d star satisfy this one. And another condition is that ratio of the lateral ranges of the inhibitory and excitatory have to be actually greater than the amplitude of the excitatory divided by the amplitude of inhibitory. And then the actually Neimer-Sack will occur. That's when the spatiotemporal bifurcation occurs before the Turing bifurcation, and the condition is actually opposite than the actually previous one. And now d have to be actually greater than d star, where d star will satisfy this equation. And the second condition is that sigma I square over sigma square is greater than alpha E over alpha I times 1 minus beta E, 1 minus beta I. This is the actually D. So then another case is that Turing occurs, actually Turing reached to its actually threshold before this actually NS, but this time K is equal to 0. That's the opposite. The Neimer-Sacker actually occurs before the Turing for K equal to 0. That's when the temporal bifurcation occurs, and the condition for this temporal bifurcation is that D is greater than alpha I over alpha E, or D is greater than alpha E over alpha I, depending on those actually conditioner. Basically, this condition gets simplified to that D have to be greater than 1. And then another case is that when actually Neymer-Seker's, sorry, this one would be actually less than sign. That was actually, typo. Turing would actually occur before Neymer-Seker for k equal to 0. This is actually bifurcation that does not give us any actually, pattern. So then finally, to summarize all of those things that we did, and a little bit more simplification is that this is actually diagram. So we use these three actually, parameters. So this S is the lateral ranges of the inhibitory divided by the excitatory. D is equal to 1 minus decay rate of excitatory divided by 1 minus decay rate of inhibitory, and in R is equal to alpha E, the amplitude of excitatory divided by inhibitory. So the first diagram showed you when actually the R is greater than 1, that means amplitude of the excitatory is greater than the actual inhibitory. This x-axis is the actually S parameter, and this y-axis is the D parameter. And we see that this actually yellow shaded area is the, where Turing bifurcation happened. And this green shaded area is actually where spatiotemporal bifurcation occurs. And this purple one is that where the temporal bifurcation occurs. And this gray part, this is where that no bifurcation occurs. As you can see here, that for Turing bifurcation, this yellow shaded area occurs only when S is actually greater than 1. Okay, D could be any actually value. For this spatiotemporal, this green shaded area occurs when D is greater than 1. That means beta I is actually greater than actually beta E. And the same thing is also true for the temporal bifurcation, that D have to be actually greater than 1. If we actually consider R is less than 1, so now actually in alpha I is greater than alpha E, then this is what we get here. We still see that the same actually condition for the Turing bifurcation, that this parameter S have to be greater than 1. Also the same actually condition for the temporal as before. Only thing changes this spatiotemporal bifurcation, where we can see that this time spatiotemporal can occur. There is actually a possibility that it will occur when D is less than 1. And in also for actually R equal to 1, these results are similar to the R is actually greater than 1. So the last thing what we will do is that we will show you the simulated pattern now. This is the first actually pattern. This is the Turing bifurcation. This is our simulated actually pattern that we get. You can see that those are actually vertically striped. That actually matches with this pattern of Lyra, Nika. Second one is the temporal bifurcation. That will actually give you this in horizontal line. And you can see that actually that stripe kind of like matches with this shell pattern. And then now those are the spatiotemporal bifurcation. Bifurcation occurs on this space, also on the actually time. You can see this actually meshed checkerboard like actually pattern, that kind of like you can see that this shell also have actually checkerboard, those actually boxes. Then those are the actually spot. This is also spatiotemporal bifurcation. Those are actually spot actually in occurs, which kind of matches those spot that we see in the actually Tigrina. This is the actually pattern we get for spatiotemporal, where we actually give some perturbation along the x. So we actually perturbed or give some noise to the x. Especially this is actually pattern we get. As you can see, those thick vertical one kind of actually matches with the actually pattern that we see in the hectica. Those are the three patterns we actually generate by actually adding the frequency gradient in alpha E, that is amplitude of the excitatory neurons. We actually add the actually cosine gradient on the actually excitatory neurons, and now you can see that those patterns show some type of actually wave, and the middle one is a little bit actually, complicated actually, wave you can see. And you can see the actually corresponding shell picture that's kind of look actually similar to those actually, pattern. This is from the excitable system. You can see this spot more like circle shape that kind of like, match with this, pattern. If you change the actually decay rate of the excitatory a little bit, that circle in the next picture, you can see they can kind of like look like actually in a crescent shape. That more actually, look like the, a pattern that we see in the Johnston eye. This is the when our response function is bump nonlinearity, the phase analysis is more actually chaotic in those cases. So we actually get the actually pattern is also very actually complex. This pattern that we got, this one we did add some actually perturbation on the actually time, and this is where we got the zigzag type of actually pattern, which kind of look the same as the Leon concha. The second one looked like more like actually, wave. And the third one, we have very actually irregular block system here, and they are look like more like stratus. And then more for actually bump linearity for the first and the third picture. Again, we add some actually perturbation on temporal actually perturbation. We got this defined type of zigzag we can see, and this actually middle one is more look like fractal type of pattern that we got, kind of look like the conus amoralis. So in conclusion, the actually model that we derived, there are actually neural model that that has been actually developed by actually Bart, Armantrout. This model that we propose, some of the novelty of our actually model is that that is different than the previous neural model, is that our model does not rely on the refractory period. So the pigmentation is directly related to the neural activity. The second thing is that we use a single nonlinear response for both excitatory and inhibitory rather than using separate response function, and that reduce some number of parameter that we have to use for our model. And our bifurcation analysis shows that a spatial pattern or Turing bifurcation occurs when the actual spread of the inhibitor is larger than the spread of the excitator. And the spatiotemporal instability usually occurs when the decay rate of the inhibition is very high. Also, spread of the inhibitor is actually very high. Considering the fact is that excitatory cells concentration is very high. If excitatory cells concentration is low, in those cases, the actual inhibitor can have slow actually diffusivity spreading in order to actually produce spatiotemporal instabilities. And for temporal instabilities, the actually decay rate of the inhibitor cell have to be actually higher than the excitatory cell. So that's mean if the inhibitory cells has a slow decay rate or the spread of the inhibitor cell is slower, that's when no pattern actually emerges. Okay, so those are some of the references that we use, the main references that we use. So I think I'm almost at the actually time 5:15. So I will stop here, and I will actually welcome any question if you have.